Hello, everyone. Today we are going to talk about applications of statistical process control, SPC. SPC is one major statistical tool to monitor a sequential process. SPC handles a fundamental research problem when analyzing data in a given application, which is to monitor the underlying sequential process of the observed data to see whether it is longitudinally stable or how its distribution changes over time. SPC charts have been developed and used mainly for monitoring production lines in the manufacturing industries during the past several decades. Today, SPC can become a powerful tool for handling many data-rich applications that are beyond the production line monitoring. This lecture introduces some classical applications of SPC and solutions developed by major industry players and their usages, and discuss some research topics of SPC using artificial intelligence in data-rich applications. A traditional SPC chart can be roughly divided into four categories: Schwartz chart, cumulative sum, QSUM chart, exponentially weighted moving average, EWMA chart, and change point detection, CPD chart. Some of them are designed for monitoring multiple quality variables or quality variables taking binary count or categorical values. Here, let me introduce a part of applications of traditional SPC chart. To detect the occurrence of disease, SPC chart have been widely used in the medical healthcare area. For example, here, EWMA chart was applied to monitor the number of patients and to detect the occurrence time of influenza. We can also use SPC chart to identify the cause of the increase in post-operative infection rate. For example, SPC chart served as a tool to make a decision whether the new surgeon was the cause of post-operative increased infection rate or not. The livestock industry utilizes SPC charts to monitor some factors related to livestock ratings, like weight, in order to improve productivity and quality of livestock. Because of the importance of SPC, many industry players developed their own analytics solutions and operate them to monitor the status of quality and to improve the quality of their products. For example, LG CNS provides smart manufacturing platform, Factova, to maximize process efficiency and minimize defect rate based on big data and AI technologies. It was reported that Factova shortened the planning time by 2 to 3 months and improved the accuracy of fault detection up to 99.7%. CJ Olive Networks developed their own smart factory solution called Factory One. Factory One has been successfully implemented in the various industries such as bio, beverage, food, meat processing industries. Samsung SDS developed AI-based analytics platform called Brightix AI. The platform has many use cases. For example, South Korea electronics assembly manufacturer built an integrated data warehouse and Brightix AI platform together, and it succeeded in reducing quality costs and enhancing shipping controls by proactively responding to defect. In the era of Industry 4.0, changes toward data-rich environment in the manufacturing are accelerating the development of new SPC methodologies. Unlike the past, where only products were monitored, quality improvement tended to require not only the product perspective, but also the enterprise perspective, with enhanced integration of the production systems. There are attempts to define how SPC works under smart manufacturing. The authors of this paper defined intelligent quality control systems and explained the concept of it. They argued that the concept will replace the traditional QC system in the manufacturing processes as automation take over most of operational tasks that were routine tasks performed by humans. That is, in smart manufacturing, monitoring and scheduling are possible based on data collected in real time instead of sampling plans and inspection. The new SPC, referred to as smart quality control by the authors, is mainly executed to physically manage various smart machines or tools through a cloud-enabled platform. These technologies are capable of communicating both with the product and their environment. In recent years, SPC has found many data-rich applications, including those involving a large number of quality variables, processed with image or network data, and more. To properly handle such applications, many new SPC methods have been developed in the literature. Some representative ones are described in this lecture. Semiconductor manufacturing is a complicated process with a series of steps as demonstrated in this figure. At each step, observations of many quality variables are collected and monitored regarding the physical or electronic properties of product or its components. As an example, in a real semiconductor manufacturing data set maintained by UCI machine learning repositories, observations of total of 590 quality variables are collected. To handle them, only multivariate SPC chart would become ineffective when the number of quality variables is large, partly because all quality variables are treated equally and those they cannot react promptly to shift in a small number of quality variables in such cases. Also, their computation when monitoring high-dimensional processes is so intensive that they become inappropriate for such applications. To overcome such limitations, recently, several multivariate control charts have been developed for monitoring high-dimensional processes. For example, this paper considered the adaptive lasso penalized likelihood function to select a small number of important quality variables among many. In recent years, many deep learning-based methods have been developed, and there were attempts to enhance SPC to be more effective and efficient for process monitoring in data-rich applications. Among them, I will briefly introduce how convolution neural networks, CNN, and generative adversarial networks can be used with SPC to conduct the following tasks, such as condition monitoring, effective feature extraction, useful information generation, high-dimensional monitoring, mitigating class imbalance. This example is about condition monitoring. As a sensor technology is developed, different sources of data can be utilized for process monitoring. process features such as sounds, vibrations, images can be used to determine if something is wrong in the process. This is an example of sound-based monitoring system that enables tracking of multiple equipment operation at the same time and detect abnormalities. Effective feature extraction from complicated data is essential part in process monitoring. In supersonic combustion technology, monitoring the combustion mode is critical for the safe and stable operation of the engine. The authors of this paper applied CNN to extract meaningful features from pressure sensor arrays to predict the combustion mode of a combustor. Here is another example for effective feature extraction. A natural control chart pattern usually correspond to the specific factors in the manufacturing process. So the control chart have become important means of the statistical process control. Therefore, an accurate and automatic control chart pattern recognition is of great significance for manufacturing enterprise. In order to improve the CCPR accuracy, there was an attempt to extract unnatural control chart patterns using CNN. Deep generative models like variational autoencoder are a popular approach to extract features from the latent space for anomaly detection. This provides a systematic way to reduce the data dimensionality. In this paper, CNN and VAE are used together to extract features from images and reduce their dimensionality. In fault diagnosis, engineers may face the situation where lack of enough useful information in the input signals to conduct accurate classification. To solve this problem in varying fault diagnosis, the authors of this paper proposed a multi-scale cascade CNN to utilize different signal scale input layers in CNN by adding a new layer before convolutional layers to conduct a new signal of more distinguishable information. A recent study proposed an improved CNN with a weighted softmax loss called the DNCNN for imbalanced fault classification. Their idea is to modify the loss function so that the softmax loss reflects class imbalance using weight. As a result, DNCNN not only learns better features than the commonly used CNN, but also deals with the imbalanced classification problem more effectively. To solve the imbalanced data problem, deep generative models can be used as well to generate synthetic data in the way to mitigate the imbalance problem. In this paper, authors proposed a defect generation method to augment the training image set based on generative adversarial network. Today, we talked about some classical applications of SPC and solutions developed by major industry players and their usages, and discussed a part of research topics of SPC using AI in data-rich applications. In particular, AI can help improve SPC chart in data-rich applications. There is a lot of research going on in this field, and there are many potential research topics. Thank you.